So, in this video, we're asking the question, if we roll two fair six-sided dice and add their values, what's the probability of rolling a 7? Well, we discussed this problem in a previous video, and we talked about how a naive approach gives you the wrong answer. The naive approach would be to list the sample space as follows. Here's our sample space, all possible outcomes. Well, when I roll two six-sided dice, the smallest number I can get is a 2. I can roll two 1s. I could get a 3 by rolling a 1 and a 2. I could get a 4 by rolling two 2s. I could get a 5 by rolling a 2 and a 3, etc. I can roll all kinds of numbers here. And the largest number I can get is a 12, because I can roll a 6 and a 6. So these are all possible outcomes. And in the previous video, we talked about one mistake that someone might say, well, the probability of getting a 7, to compute that, what I'll do is I'll see how many of these things equal 7. Well, only one of them. Count 1. And then I divide by the number of things in the sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I might think that this is my answer. But we discussed how this is not the right answer. And the reason that's not the right answer is because the method that we're using here depends on all these outcomes being equally likely. But they're not equally likely. For instance, how many ways can I roll a 2? Well, the only way I can get a 2 is by rolling a 1 and a 1. There's only one way that can happen. So a 2 is not very likely. However, how many ways can I roll a 7? Well, I could roll a 1 and a 6. I could roll a 2 and a 5. I could roll a 3 and a 4. There's several ways to roll a 7, but there's only one way to roll a 2. So these can't be equally likely. 7, for instance, is more likely than 2. So we can't use that rule that got us 1 over 11. That rule is not guaranteed to get us the right answer. So what we need to do is we need to view the sample space in a different way. So this is the trick for this problem. And the way we're going to do this is we're going to imagine that we have two differently colored dice. Oh boy, this one is not showing up very well on my green screen because it's a green die. But anyway, you get the idea. There's two differently colored dice. And so if we think of the dice this way, we can imagine the sample space a little bit differently. So what I'm going to do is I'm going to depict each die's value separately in a table. So let's go ahead and write this table out. So we're going to have the columns of the table representing the value of one die, and so we'll call that die 1, and then the rows representing the values of another die. Right? I think I said that backwards. So the rows are going to be die 1 and the columns will be die 2. All right, so what are the values that I can get for die 1? Well, I can get 1, 2, 3, 4, 5, or 6. What are the values I can get for die 2? Well, 1, 2, 3, 4, 5, or 6. Okay, let's fill in this table by adding the values of the dice, because that's what we're doing in this experiment. Okay, so I have written inside the table the sum of the two die values. I've added them together. Now, what I'd like you to observe is that the outcomes, each outcome in this table, is just as likely as any other outcome in this table. These outcomes are equally likely. Why is that? Well, because these are all equally likely. These are all equally likely. So a given combination of them, say a 4 and a 3, is just as likely as any other single combination of them. So these outcomes inside the table are all equally likely. So now that we have a sample space of outcomes that are equally likely, we can use the approach that we tried before, using this as our sample space. So this square of sums, this is our sample space S. Now, what is the probability of rolling a 7? Well, how many ways can we get 7? 1, 2, 3, 4, 5, 6. How many things are in our sample space? Well, there's 6 this way, 6 that way, so there's 36 total things. 6 out of 36 is 1/6. I can compute other probabilities. What's the probability of rolling a 5? Well, there's 1, 2, 3, 4 ways to roll a 5 and 36 possibilities. That's 1/9. And what's the probability of rolling a 2? Well, there's only one way to roll a 2, and there's 36 possibilities, so it's 1 out of 36. So this is a kind of a trick approach to deal with a problem that initially we didn't have equally likely outcomes in our sample space, but what we did is we were able to rethink the problem and write down a sample space where each outcome is equally likely. And that enabled us to solve the problem.